There we go. So just to start off, announcements like usual. The first thing that I want to point out is it's that time of the year again where you go through and you review your professors. You should have gotten an email, according to what I'm hearing, that should direct you to basically your class evaluation. I need to have you guys fill that out at some point between before I believe it says the 20th, if that's possible. Does anybody have any problems with that? Like they didn't get the email or something?
I think mine's been popping up on my Brightspace.
Yeah, mine too, I think.
Perhaps it's there. Okay. With that said, yes, I did just post another lab for you for this week. Yes, I did just post another quiz for you this week. So please remember to do them. If you have questions, as per usual, I will be available after class time to answer any questions you might have until 9 when we usually had lab end. Okay, so with that done, let's start up by just a real quick review of rotation, which is what the quiz is on. A overview of what I kind of went over with the extra time last time. And then we are moving into ideal gas laws. I believe next week will be when we start doing waves and that sort of fun. Okay? So before I get started, any questions?
I'll have a question about the quiz. I'll need to talk to you offline about.
Okay.
That can be after the lecture.
Okay, that'll do. Well then, with that said, just a quick review of rotation. There's the eraser. Okay, so we said that the key thing to remember with rotation for the vast majority of it is that there's a nice set of variables that you can just convert back and forth with, and you already know what the equations are. It's just the kinematic equations again, it's just the energy equation again, it's just momentum again, etc. They just have different names because of the different because we're in rotation now instead of linear motion. So anywhere that you saw v before, it's now omega for angular velocity. Anywhere that you saw x for position before, it's now theta for angular position or angle. T for time stays the same. A for acceleration becomes alpha for angular acceleration. F for force became torque, tau. Okay? P for momentum became L for angular momentum. And M for mass became I, which we call the moment of inertia, right? And so just for example, one of the common equations that you might see is that where before we had the final equals the at the start plus AT, well, this now becomes omega final equals omega at the start plus alpha T. Make sense?
Yeah, that's fine.
Cool.
Yeah.
There are a couple of slightly new equations. One that you should recall from the previous quiz is that tau equals F times R times sine theta. Okay. Another one that, one of them that's new is that I, for the most part, is going to be equal to M times R squared. Okay, that is to say that an object's effective mass depends on where the distribution of the matter. Okay, where the material is, what the shape of the object is. There's another very, very important one, and that has to do with going around a circle. If I want to know what distance, the booklets call it S, around the edge of the circle I've traveled from some starting point here to some ending point, I can convert back and forth between the angular value and a linear value if I know the angle and r, or rather s, theta, r, etc., where the equation is I just wrote that backwards. Theta times r equals s if theta is in radians. Okay? Now, because of this equation right here, we have the same equation get back and forth between velocity, angular velocity, the same equation get back and forth between acceleration and angular acceleration. So those ideas should kind of help you moving forward through that quiz. Now then, picking up where I left off last time. We had talked very briefly about expansion before I kind of said, okay, have a nice night, and then we had that extended thing. So let's talk a little bit more in depth about expansion due to heat. We'll go over what's called the method of mixtures, where I have a slight negative sign mistake at first, and then I suggested that you should just stick with Kelvin because it makes it so that you avoid any negative sign errors. But we'll go over those right now. So the first thing that we deal with is going to be thermal expansion or contraction. I had mentioned that a lot of materials will expand when they heat up. And we talked about the idea that it's because the particles need to be further apart, etc. Now, the overall effect is generally fairly small, such that if I have, say, a rod of metal that is yay long, I would end up needing a micrometer in order to measure how much it would expand by if I only have the temperature increase by, say, 10 degrees. Often, the value that I'm going to be looking at is something times 10 to the negative 6 for my, or lower for my coefficient. Now, with that said, what coefficient am I talking about, and what's the equation that's involved with this? Well, I'm going to over-exaggerate the expansion a little bit so that you can see what's going on. If this distance here is L naught, the length of the rod at the start, and expanded by this much, such that this total distance to the end of the expansion as well is L, okay? Then we expect, did I say something silly? Just a second. Yes. Correcting myself. No, we just want that short distance, delta L. Then what we expect to find is that delta L is equal to some constant, which in this case gets the variable alpha, okay, times L naught, the original length, times delta T, okay? How much the temperature changed by. Now then, that's interesting, but one of the major things to take away here is that this is usually very tiny. Okay? Okay. So why did I emphasize that? Well, let's look. We already know that things don't just expand linearly. I can have a, say, sheet of paper expand, and it's going to expand both in X and in Y, correct? Well, how does that end up working out mathematically? Well, what ends up happening is, say, this expands in this direction, but it also expands in this direction. And finally, I have a little area of overlap here, okay? And what we're going to find out is that that little area of overlap, we end up ignoring. So how the math looks is this. I have, so if that one's I'm going to call L, I'm going to call this W naught, and this delta W, such that when I look at my change in area, delta A, it's going to equal, in order to find delta W, I need W naught times alpha times delta T. In order to find delta L, I need L naught, right? But wait, do I want plus here? Let's think about what's going on. When I have this expand, right, I'm not only having this length change, but if I'm looking at the area, I have basically this entire section growing. And so it's not just W naught times alpha times delta T. If I'm looking at the area, it's actually L naught times W naught times alpha times delta T. Here I get an extra W naught for that width there changing, okay? Where from what I described, this one is delta L and delta W. That's these two sections. What about this section? Well, it's going to be these two basically multiplied by each other. And I get something on the order of plus W naught squared, L naught squared, times alpha squared delta T. Uh-oh. This is where things go screwy. If this is already something times 10 to the negative 6 or lower, then alpha squared is going to be something times 10 to the negative 12 or lower. And we end up saying that this we can just ignore, okay? Now, I also want to point out one other thing. Look here, L naught times W naught, that's just A naught, however much area I had at the start. And I have the same thing over here, such that what this really reads is two alpha times A naught times my starting area times my change in temperature, okay? Interesting. By the same sort of argument, I can get that my change in volume through expansion should be simply the same idea, but 3. Okay. Now, there are a couple of times where this sort of term here is non-negligible. If you have some material that you can significantly heat up without it simply melting and making this invalid, then that would be important. But that would be really hard. Alternatively, if you have a really, really large area, that term might be important, okay? Something that's, say, like, I don't know, the giant metal sheet that is on the front of the science building as part of the decoration. That you might want to consider that term for, simply because it's going to be expanding by a decent amount. Because L naught and W naught are so large. Any questions so far?
No, it's all pretty good. I'm good
Cool.
with it.
Well then, with that said, next thing I want to talk about is what the book calls the method of mixtures. And this is what I kind of went over time last time for, which goes like this. Let's say I've got some container. In general, I have two different materials that come into contact, and I want to find out what the final temperature will be. To keep our lives easy, let's make it ice and water, because they're things that we're familiar with. So I've got some water, and into the water, I drop a cube of ice. Okay, so give me a starting temperature for the water.
Let's do 45 degrees.
Okay, that's really warm water, but okay then. So
we're going Celsius?
45 degrees Celsius, which is going to be, when I convert it to Kelvin, because as I kind of mentioned at the start, in order to keep your life easy and not make negative sign errors, I strongly suggest doing this in Kelvin. So that's going to be plus 273. So that's 318 Kelvin. Okay. What temperature do we want the ice to start at? It's got to be something below freezing.
32 degrees.
Negative 32. Okay, that's some mighty cold ice.
I didn't say negative, but that's fine too.
Okay, so just note that I'm doing things in Celsius, so 32 degrees would be above freezing if we were dealing with Celsius. Okay, let's see. So 273 minus 2 gives me 1. 70 minus 3 gives me 4. So 241 Kelvin. Okay. Now, I'm just going to make our lives easy, say that this is 100 grams of water and 10 grams of ice that I'm dropping in there. Okay? Any questions so far, just with the setup? No.
So what was the, so I know it's 10 grams of what?
Ice.
Ice?
I will say the green marker is really hard to read.
Yeah.
Oh, okay. There it is. How about the purple?
That's even worse.
That's even worse. Okay. We will stick with the black then. So yeah, that's 100 grams of water, 10 grams of ice. Okay. With that said, the key idea with this method of mixtures is that because thermal energy is a type of energy, we can apply conservation of energy. That is to say, whatever energy the water loses because it cools down when it's in contact with the ice, right? that energy the ice will gain, okay? That is to say, delta E water, negative, because it's losing it, equals delta E ice. Does that make sense? I'm going to go with yes, because that's something that we've kind of talked about briefly already.
Yep, that's.
Well, the good news is, as we said before, we have an equation for this from when we were talking about specific and latent heat. Namely, we know that delta E water should be so all negative, so this is the water side, has to equal now, I've just written C and I've just written L because to make things easy, I've chosen ice and water, which are actually the same substance, right? If it was different materials, if I say had, I don't know, water and salt, okay? I would have to have different values for C and different values for L for the two cases. Does that make sense? Because they are different materials, they will have different constants for their specific and latent heats.
And what does the C and the L stand for?
C is the specific heat of the material. It's how much energy per degree the material needs to absorb in order to basically, in order for its temperature to go up by 1 degree. L is the latent heat of the material. It's how much energy it takes to convert 1 kilogram of the material from either solid to liquid or liquid to gas. But remember that most materials have a different constant for solid to liquid than they do for liquid to gas, okay? So in this case, it would be the latent heat of fusion, which is what we call it when we're going back and forth between liquid and solid.
Okay.
Any other questions?
I think we did.
Okay. So then, with that said, we can put in our information. Now, we have some rather large numbers for how high the temperature is here and how low the temperature is there. So I honestly don't know what's going to come out as the final temperature yet. So this might get a little bit awkward with these two terms. But let's just start with figuring out what we should do. The key thing here is that I expect them to continue changing temperature until they reach thermal equilibrium, which who here can remind me what thermal equilibrium, what is true when two objects are in thermal equilibrium?
They're the same temperature?
They're at the same temperature. Excellent. That is to say that the final temperature for both materials should be the same, okay? So, just plugging in our numbers, I should get, the specific heat of water is, if we are using kilograms, it's 4,190, but we are using grams, so it's 0.419 times TF, which is what we're looking for, our final value, minus the initial, which is what we chose up here, so 318 plus 100 times L, but I'm going to put a little question mark there because I'm not sure which one's going to melt and which one's going to freeze because of those numbers there. Equals the mass of our ice, 10, times 0.419 times this basically again, but with the appropriate starting temperature, TF minus 241. Sorry, running out of space. Plus 10L. Okay. So from here, what's going to have to happen is I'm going to try to simplify this as much as possible. Right, I should also mention L is 80. Okay. So, give me just a second to remember how to figure out. Okay, with that much more water at that much above freezing, I can tell you that what's going to happen is all the ice is going to melt. I'm just going to drop this term because in order to basically solve what's going to happen between the two of them, I would need another equation, and I'm not going to throw something that complex at you on the quiz, okay? So I'm just going to drop this term altogether because I know that the ice is going to melt. Make sense? The water is not going to freeze.
Okay.
Any questions about that?
So because we had the water or the ice cube so cold, technically per the equation, it would have frozen the water.
No. So look, we are at 45 degrees above freezing here with 100 grams of water. We're at only 32 degrees below freezing here for 10 grams of ice. So that water can absorb a lot more energy than the ice. I just said that backwards. That water can give a lot more energy away than the ice takes before it reaches freezing. Does that make sense?
Yeah.
Okay. So I'm just eliminating that term. So, because I've run out of space, I'm going to erase this stuff up here, okay? I've already put all that information in.
Yeah.
So, coming back up, I get that. I'm just going to start simplifying these numbers. From my 10 times 80. And don't forget your negative. Okay. Plus 10 times that is 4.19. Then do something silly. Yes, there's a decimal point here. Okay. Then what we really want to do is get TF on one side by itself. And so I'm going to have to further simplify this and distribute, but for that I need the calculator. So this times this gives me this number comes from multiplying these two together. This is this. Then multiply these two together. and then add 800, and I get negative 209.8, just to add the point, so 0.2, and plus okay, but TF is still not on one side by itself. I'm going to move this over to here and this over to here, such that I get negative 46.09 TF equals this huge thing. Okay, and at that point, all I have left to do is divide both sides by this number to get 293.6 Kelvin. Now, because this is bigger than 273, which I suggested it would be, right, which was freezing, I know that all of my ice melted, like what I expected. I know that the temperature of my ice increased substantially. It went from 241 all the way up to 293. And my temperature of my water went down a bit as well. It went down from 318 to 293, okay? So a common thing that might be asked would be, well, what was the change of temperature for the water? Well, then what I would do to get that change in temperature is I'd simply say that was this term here, that's this here. So I'd say my 293.6 minus 318, I get that it was negative 24 Kelvin. Or because Kelvin and degrees Celsius are the same, they just have a different starting point, it's also negative 24 degrees Celsius. But my strong suggestion is for this, so that your equation for change is always simply delta T equals TF minus T I final initial stay in Kelvin. Okay. Now I heard the start of a question. What was it?
So what was the last point that you used to be able to find a change in temperature?
Well, it's exactly this. Okay.
Okay.
So I said, well, if I look at my water, right, my change in temperature for the water, TF is what we just solved for, and
Okay.
T18 was the starting temperature. You subtract those from each other, and you get negative 24.
Okay.
Okay, any other questions? And so it's all about this conservation of energy here. Okay, where whatever the water loses is what the ice gains. Excellent. Now, there's one more thing that I want to point out for you. It's the last thing in this chapter before I move on to the next. And it deals with how things like refrigerators work, okay? So the big question that I have is, what is cold? What does it mean for an object to be cold? Ideas?
What does it mean for an object to be full? Are you saying
Cold.
full?
Cold. C-O-L-D.
Oh, cold. That's relative.
Well, okay, you can say it's
Well,
relative, but aside from the issue that it's all relative to something else, what else does it mean for the object to be cold?
it's cooler than room temperature.
Okay. Any other ideas? Anything you want to expand on that with? This is true. This could be true if you're using room temperature as your reference point.
Colder than freezing?
Yes, we could choose a different reference point, but let's not use cool or cold in our definition is kind of what I'm getting at. That makes it a bit cyclical. Anything else we want to add?
Not hot.
Not hot. Okay. So in general, what I'm understanding that you're trying to get at is that the temperature is lower, correct?
Yeah.
Okay. And we said that temperature was all about average average velocity of the particles. And so if the temperature is lower, the energy contained is lower. So what I would like to point out is that cold deals with basically the relative amount of energy present. Cold is not its own separate entity like heat, if you will. Heat is what we call the transfer of this thermal energy, whereas cold is simply a description that we have of something that is lacking compared to something else in thermal energy. Okay? So with that said, how does then something like a refrigerator work? What does a refrigerator do? Any ideas?
It's a dehumidifier.
Yes, that is one of the ways that you can go about it, is make it basically be a dehumidifier. Any other ideas? Anything else that you want to add?
Does it use, like, are you talking about like it using refrigerant to replace the heat energy in the refrigerator with cooler?
Okay, you just made the exact mistake that I was trying to point out earlier. You can't put cold into anything, okay? All you can do is remove heat, okay? So what's going on with a refrigerator, and the way to think about it is that it is a heat pump. Now, the way that you accomplish that, there are a couple of different ways that you can accomplish that. One is basically to have a dehumidifier, where basically you have condensation occurring, which allows the heat to be transferred out of one of the materials, namely the material inside the refrigerator, and it's transferred to the surrounding environment. Let me say that again. The heat inside of the refrigerator is transferred to the surrounding environment. You see, conservation of energy still has to hold true. The heat, the energy that you pull out of the refrigerator, it has to go somewhere. It goes out of the refrigerator into the surrounding environment. In fact, that's why they say holding your refrigerator open does not make the room colder. It might make the area directly around the open door colder, but it will not make the room colder. It actually makes the room hotter. Okay? Because you're pulling all the heat out of the fridge and putting it into the rest of the room. Plus, unfortunately, there is no such thing as a 100% efficient motor, so you're putting the extra heat from the motor into the room as well. So the big takeaway from that discussion is that you can't put cold into anything. You can simply take energy out of it. You can take heat out, okay? And that things like a refrigerator or the like, or an air conditioner, they are heat pumps. questions? Yes, no, a little bit.
I think I'm good.
So cold is just the absence of heat.
Cold is the absence of heat, yes. Absence of thermal temperature, to be specific, because for historical reasons, we say that heat, which gets the variable Q, is my change in energy, not the energy present. So technically speaking, absence of thermal energy. Any other questions?
No. Good.
Okay then. With that said, let's then move on to the next chapter. So the next chapter plays around with a lot of thermal ideas still, but the key topic of the next chapter is what we call the ideal gas law. I greatly prefer to introduce it through the ideal gas law instead of break it down into its components, Charles and Boyle's law, because I feel that having one equation instead of several makes life easier, right? So the first thing that I have to talk about before we discuss what the ideal gas law is and what the equation for the ideal gas law is what is an ideal gas? Well, if you recall from that simulation that we had earlier that I put up on the screen share, we saw that when I had a gas inside of some container, it basically looked like a bunch of particles moving around, more or less at random. They could hit the edge of the container and bounce off, right? Or they could hit each other and bounce, but they're just kind of flying around at random, right? One of the key differences between an ideal gas and the gas that you saw in the simulation is that there is no interaction, okay? That is to say, there is no attraction force between the particles, okay? If they hit directly, they can still bounce off of each other, but there is no interaction in general between the particles, okay? They are not attracted to each other. That is an ideal gas, a quote, perfect gas. Any questions about that idea? No. Okay. Then with that said, the vast majority of any temperature changes are going to occur because the particles are colliding with the wall. They are interchanging energy with the walls of my container, okay? But it turns out that there's a couple of different ways that it can do that. And it's all based on this idea of the change of momentum the particle will feel when it hits the edge of the container, and what we call the mean free path. How much space there is in between the particles before they end up hitting each other. Okay? And the issue goes like this. When the particle ends up colliding with the wall, okay, it's going to bounce back, and it's going to have a momentum change that's basically double whatever the original value is, because we're having it be a perfectly elastic collision, and no kinetic energy is lost. If I were to say shrink my container, would you agree that now the particles have less space that they can move around in before they either hit each other or the wall?
Yes.
So they have a lower mean free path. They are going to collide more. often with either the wall or each other, and they're going to transfer energy a lot. Okay? All these should sort of make sense. And what we will see is that because they are colliding more often, just like we saw in that simulation, and I'll pull it up again in a moment, because they're colliding more often, you'll end up having effectively a larger force on the walls of the container, okay? Because there's more collisions, there's a larger average force. And what did we say force distributed over an area is? What is the name for force distributed over an area? Starts with a P. PR.
Pressure.
Pressure, okay. So one of the things that we're going to deal with this ideal gas law is pressure. Because I was already talking about the fact that we're changing the size of the container. Another thing that we're going to deal with is volume, okay? And it turns out that the pressure and volume end up being related to each other. If I increase the volume, I've got more space for these particles to move around in. They hit the wall less. My pressure decreases. If I've got less space for the particles, yes, okay. If I have less space for the particles to move around in, they hit the wall more often, right? The pressure goes up. Any questions about that?
Repeat that again.
Yes. If I've got more space, like the black box for the particles to move around in, they will have basically collisions with the wall less often, simply because there's more space for them to move before they hit the wall again, right?
Okay.
And so the pressure will be less. If I have less space, like the green box, just the exact opposite situation, the pressure will be higher if I have less space.
Okay.
Make sense?
Yep.
Excellent. Now, there's a couple of other factors that determine how often those collisions happen. Another way that I can reduce my mean free space, reduce how much distance the particles can travel before they either hit each other or the wall again, is I can simply add more particles, right? More particles, they'll hit the wall more often. I'll see an increase in pressure, right? Make sense?
Yep.
Another thing that I could do to make my pressure increase, simply because these walls are being hit more often, one, but also because they're going to get hit harder, is I can make my particles go faster, okay? But what did we call the average, a term that deals with the average velocity of all my particles? Last chapter. Starts with T, TEM, temperature, right? Okay. So if I increase the temperature, the particles will be moving faster. They'll hit the wall both more often and they'll hit the wall harder. This also results in the pressure increasing, okay? And why do I keep on talking about the pressure? Well, going back a couple of chapters to Bernoulli's law, we said that pressure is like my energy density, how dense my energy is, how much energy I have present per unit area. And so a lot of what we're going to be looking at, again, it can be looked at as energy conservation. My amount of energy that I have present has to stay constant, okay? And so I started by writing up P times V for a reason. That is to say that if P is my energy density, if I then multiply that by how much area I have, how much volume I have, this is my energy, okay? Make sense?
Yep, got it.
Cool. Well, then there's another way that I can figure out how much energy is contained in this box. And I kind of just went through the various different factors that deal with it, okay? We did talk about pressure and volume, but the other two that we mentioned were if I can look at how much energy the particles contain. Which is going to be described by basically the mass times a constant times the temperature, okay? Now, here's the one way that things go a little bit screwy, okay? And that's that, although when we talk about the energy of a particle that's moving, we deal with something like 1/2 mv squared. When we're talking about the ideal gas law, we don't directly deal with the mass of the particle. We end up actually absorbing the mass of the particle into a constant, okay? Instead, we deal with how many particles are present. Okay, then. And we do that in one of two ways. We either deal with how many moles particles are present, or the actual direct number, okay? If we are dealing with the direct, oh, wait. Just let me double check that I don't get this backwards. Not the way I wanted it expressed. Okay. We'll just write it this way then. If we are dealing with the actual number of particles, okay, times their corresponding mass, we will get that my pressure times my volume, which is E, equals N, the number of particles, times the mass of each particle, times still a constant, because we need to know how much energy per unit of material there is for that particular material. Remember that entire thing called the specific heat, right? Well, for an ideal gas, the way that we can look at it is the specific heat is what we call Boltzmann's constant, which gets the variable case of B, okay? The value of it is, there we go. 3/8 times 10 to the negative 23rd. Okay, times T, but most descriptions of this ideal gas law absorb a couple of different things. And instead of dealing with the actual direct number of particles, they deal with the moles, which deals with Avogadro's number. Okay, such that the commonly stated version of the ideal gas law is P times V, which is the energy on one side, equals N, the number of moles you have, times R, which is a constant that basically absorbs all those other terms, times T. Okay? Okay then. in order to find n, you take your actual number of particles, divide it by Avogadro's number, and I forgot to write that, I'll get to that in a second, and you get your number of moles. Avogadro's number is, I always forget. .02, okay. Right, green, not good. 6.02 times 10 to the 23rd particles. Okay. So the entire idea with the ideal gas law is, again, energy conservation. Okay, and the real law that we're going to deal with, the one that we're going to see a bunch of times, is this one, PV equals nRT. Okay, and because we're dealing with the one with moles, and to keep our life simple, we're going to do Kelvin. R should be 3.81. Any questions?
No.
Really? Because this equation right here has some very interesting side effects. For example, what would happen to the temperature then, according to this equation, if I kept my pressure the same, but reduced the volume of the container?
Would it decrease?
Just speak up, couldn't hear you.
The pressure would increase.
Wait. Let me say that again because it sounds like people misheard. If I keep the pressure the same and reduce the volume, what ends up having to change on, say, this side in order for that to work?
Right, temperature decrease.
Again, just speak up.
Wouldn't the temperature decrease?
Aha! So wait, that means that there's another way to change my temperature when I'm dealing with gases or when I'm dealing with materials in general, okay? Basically, I don't only have to have two objects in this thermal equilibrium, have them in thermal contact in order for my corresponding temperature to change. I can also accomplish it by allowing them to expand or compressing them, okay? So what we end up seeing is that, in general, compression tends to cause things to heat up, and expansion tends to cause things to cool down, okay? That is, if we allow it to expand and have the pressure change as well. There are a couple of different versions of what we call the different processes when we're keeping one of the variables constant and changing the other two. For example, what I just talked about, where I was keeping the pressure the same and changing my volume, we call that an isobaric process, which is just a fancy way of saying the pressure doesn't change, okay? A process where the volume doesn't change, but my pressure and temperature are allowed to, we call that an isochoric. If the total energy is not allowed to change, basically there's no interaction with the outside, we sometimes call, I believe that's adiabatic. But before I get into too much detail about these names, let me double check if you're expected to remember them. No. So let's not spend too much time on the names, but rather talk about what these equations mean for how things change as I basically expand, contract, and heat up or cool down the box. And the best way that I can do that is by actually going back to that simulation that I had before. So I'm going to pull that up again, just a second. Oh, I think I made a slight mistake with, I'll have to repost the lab because I think that I left something blank. I'll fix that as soon as class is done. Anyhow, so what I'm going to do here is if I do this, it adds particles to the system, right? And we see that they're bouncing around and they're at a certain pressure at the moment and they're at a certain temperature, okay? So what I was describing earlier was if I reduce the volume, I see that the pressure went up in this case, where we kept the temperature the same, okay? In general, the total energy did not change because I had a higher pressure for my smaller volume, and the particles stayed at the same temperature, okay? If I now allow it to expand, keeping the same temperature, I see my pressure again drops, right? Now, if I say I want to hold my pressure constant, okay, and allow my temperature to change, you see that slowly, along with the increasing temperature, in order to deal with that energy I was adding in, my volume also changed, right? If instead I choose to hold my volume constant and increase the temperature, I see the pressure increasing, right? Questions so far?
No, I think it's
Pretty obvious?
yeah, I think it's pretty explanatory.
Okay then, what would you expect, saying that I'm keeping my volume constant still, what would you expect to happen if I were to add more particles here? Based on the equations that were on the board, the PV equals N times R times T.
Pressure would go up.
They would bounce off each other more often, right?
The pressure would go up, they would bounce off each other more often. Anything else? Well, let's see. I see that, yes, the pressure just increased, right? In order to deal with increasing N. So is this starting to hopefully make a little bit of sense with the ideal gas laws?
Yeah.
Excellent. Because that's basically everything that was in that chapter. Instead of going through and introducing it separately as Charles and Boyle's law, I did it all as the ideal gas law. Thankfully, you guys do not deal with the actual individual components of the ideal gas law, why exactly we describe it as non-interacting gases, etc. So we will leave that chapter there. Got a little bit more time, so would you like me to basically address some questions, do some example problems, or would you like me to continue into waves?
I want to model do example problem, maybe.
Okay then. With that said, I'm gonna just pick one at random from inside of the chapter. How about, let's say, number 4 on page 420. Where did my erase it?
Okay.
I'm gonna leave that up because otherwise I'm gonna forget it. And I'll leave Avogadro's number up in case we need it. The other ones, we won't. Okay. With that said, problem says, gives me a volume, a pressure, a resulting volume, a resulting pressure, a resulting temperature, and it wants me to find what the initial temperature was, okay? So it's saying that we're dealing with PV equals nRT, okay? But what they're saying is I have some starting values and I have some final values. And provided that energy did not leave, if I change some of these values, I should basically have this entire row be equal to this entire row, okay? Everything making sense so far?
Yep.
Cool. Then let's just start plugging in our numbers. We have that V at the start is 18 cubic meters. We have that P at the start is 105 kilopascals. I'm just going to leave it as K for the 1,000. Okay. Oh, I'm sorry, I looked at the wrong line. It's 112. V at the end is 15 cubic meters. P at the end is 135. Uh-oh, that means that we didn't actually keep the energy the same, but there is something that did stay the same. T at the start is what we're looking for. And let's see, where did it go? T at the end is 235 Kelvin, okay? And what I'm going to point out here is because we are dealing with specifically the amount of energy contained, we have to use Kelvin. We can't, because we are not dealing with delta T, we are specifically dealing with the actual amount of energy contained, we have to use Kelvin. We cannot simply use the other degree systems. Does that make sense? Where absolute zero is 0 Kelvin. The point where I can't get any more heat energy out is 0 Kelvin, okay? Questions?
Oh. No.
Okay, cool. Then, there is one thing between these two that should stay the same, even if, from what we're seeing here, we're not keeping the same energy. And that thing that should stay the same is my number of particles. Because they didn't give us any information about it, we're going to say that n naught is equal to nf. Okay? Furthermore, r is a constant. It's the same in both of them because it's a constant. Okay? But we might end up needing it in order to figure out what T0 was. So I'm just going to leave it there for now. So what we're seeing is we have two equations, right? We know that somehow we have to have them end up equaling each other, right? And we've only got one unknown. How do we make that work? Ideas?
Sorry, I had to tune out for a minute. I didn't hear the question.
Ah, okay. Then before I basically give the answer, I said we got these two equations, right? We've got a single unknown. This one's completely determined, right? And I want to find some way to solve for that unknown. Any ideas of how to do this? Well, a common trick that we will use throughout this chapter is we deal largely with ratios, okay? You see, this side over here describes a ratio where I have a certain amount of energy at the start and a certain amount of energy at the end. If I divide the two, right? Well, this is also the energy at the start, and this is also the energy at the end. I should have the same ratio on this side. Does that make sense?
Yeah.
Okay. So then what we're seeing is did I write that right? No. 135. There we go. This. N cancels, R cancels. That's why I was saying you could cancel them. Let's calculate this because that'll allow us to find T. So the top gives me, yeah, that's fine. The top gives me 2.016 times 10 to the 6th. Bottom gives me 2.025 times 10 to the 6th, 10 to the 6th. There we go. I divide them by each other. I get, didn't change that much. Okay, anyhow, I get 0.9955. Okay, might be a rounding error. It might supposed to be 1. Anyhow, I come to the other side here, and I see that T is not quite by itself, right? So what can I do? I can multiply T to the, I can multiply the 235 to the other side to see what T should be. So 235 times 0.995 I get 233.9 Kelvin. Now, if that was a rounding error by the book and it was supposed to be 1, then this would actually have come out that the two temperatures were the same. That all that happened here was that my pressure increased because my volume decreased, exactly like what we were showing in the simulation. Does that make sense?
So what did you do for the second part after you got the ratio between the two?
Right, okay, so I did not write one of the steps here. Let me write the extra step. So what I did was I said my ratio between these two, after I calculated it out, was 0.9955 equals T divided by 235, right? In order to get the 230, in order to get the T by itself, I multiplied both sides by 235, such that I have 0.9955 times 235 equals T. Well, that then is this. Make sense?
Okay.
Any other questions? Okay, then a very good. No. Okay, then a very useful tool for this chapter. And you can actually apply it to previous chapters if you have a starting and ending scenario. A very useful tool is that I expect these ratios to be the same. I don't have to stay specifically to, if I have a single unknown, I need a single one equation. If I've got two equations like this, one for the start and one for the end, I can set up ratios. Questions?
Repeat what you said again?
Yes. I said that if I have one equation for the start here,
Okay.
and one equation for the end here, even if this one is completely solved, and I still have this unknown, if I don't have enough information just on this side in order to solve it, because I don't know anything about n, actually that'd be two unknowns in this case, I ended up canceling out one, I can still solve for t by setting up this ratio between the two of them such that I canceled one of my unknowns. I eliminated an unknown by having it cancel inside of the ratio. Does that make sense?
Okay.
Okay. Any other questions?
I don't think so.
Then because we are supposed to end at 6:50, I've got less than a minute. I will be available for the rest of the time until the end of the lab, till 9. But before you guys start the lab, as I said, I believe I accidentally left a certain spot blank. Let me repost the lab, okay? But yes, I'm going to end the recording here. Have a nice night, gentlemen. If you have questions, you may stay on. If you have questions that you need to ask in private, please email me and I will respond through email. Okay then.
Okay.